Hello students, my name is Shashank Shekhar and we are doing a crash course on chemistry of 45 days for the upcoming JEE exam, and today is our 21st day. So we have started the chemical kinetics chapter for 2 days, and today is the last day, and we will see today the effects of temperature and catalyst on the rate of reaction and the rate constant. So let us begin our chapter, that is chemical kinetics part 3rd. Okay, sorry. Yeah, so let us start our chapter. So before starting, I have left some part of the yesterday's lecture, so I will cover that part first. So we have not studied pseudo first order reaction in detail with examples. So today I will show you some examples to make you more to make a more realistic approach towards this concept. So let us take an example. So here is an example of the hydrolysis of ethyl acetate. So this is the ethyl acetate, and we are reacting it with water. You can say doing hydrolysis of it. Then we are getting a carboxylic acid and a alcohol. Now what is the point here I want to make that see, we have used a 0.01 mole of this ethyl acetate, and all of these have been consumed and converted into the required product. But if you see the concentration of water, that was initially 10 mole, it has not shown any significant amount of change, that is only 0.01 mole. So this change in concentration of this water is not that much reflected in the rate order. So on the, or you can say the rate law. Now due to this reason, maybe it may be affected by this concentration of water, but due to this very insignificant change in its concentration, there is no effect on the rate constant, and it's behave like a first order reaction rather than a second order reaction. So this is an example you can use to clarify it. So it is given in NCRT. So if you want to make it a point, then it is same written here. The concentration of water does not change it or altered much. Such reaction are called pseudo first order reaction. Now if you are asked that how you will write the rate constant for it or the rate law for it, then it will be a first order reaction simply. So do not get confused that it is a pseudo order, then it seems like a pseudo order. It behaves also like a pseudo order at all. So let us take another example. So this is an inversion of sugar. So inversion of sugar also involves water. So we are taking sugar and we are inverting it, getting glucose and fructose. So two products are formed here, that are glucose and fructose. And likewise in the hydrolysis of ether, we have seen that there is a very small change in the concentration of water. Here also the change in concentration of water is very small. So we can write the rate of reaction or the rate law only in terms of this sugar concentration. So it is this, and this rate is equals to K into concentration of sugar. So we have not included this water because of the insignificant concentration change. So this is also an example of pseudo first order reaction. Now let us move to our today's lecture. So we will see the effect mainly of temperature and catalyst on the rate constant of a reaction. So let us first start with what is reaction profile. So you must have seen this reaction profile or this kind of diagram in NCRT. So let me clarify what does it depict. So if you see on the y-axis here, or any, or you can say the vertical axis, then the potential energy is mentioned here. Similarly, on the x-axis or on the horizontal axis, the reaction coordinate is written. So by this diagram, we are saying that what is the change in energy as the reaction is proceeding. Okay, so this is the very meaning of this reaction profile or any other reaction profile. So basically, it is the change in potential energy or the energy as the reaction is proceeding or going from reactant to product, or say wise from product to reactant. So this is the reaction from going from A to B. Okay, so if you consider this energy barrier here, so suppose this is the energy of reactant, that is ER, and the reactant of energy of product, that is EP. So if you see the gap between this activated complex, so this is also called as transition state. So you can also term is a transition state. So in many books you can see this term also instead in place of activated complex, that is transition state. So the product reactant A goes from A to C, that is the transition state, and then goes to the product. Now, what is activation energy? It is the energy that is required to move the reactant, or you can say to convert the reactant from A to the transition state C or the activated complex C. Okay. Now, if you move the reaction further, or if you trace the energy of the reaction further, then it will go from C to B, that is the product. So this is the product. So if you now consider the energy barrier between these two, that is the reactant and the product, you can see there is a small enthalpy change, or you can see clearly that is a small amount of energy is released. So this is the only this is the energy that is called enthalpy change during a reaction, or you can also tell it as delta RH also in terms of thermodynamics specifically. So this term is called as delta H, or enthalpy change for a reaction. Now what you can see from the this enthalpy change is that since this enthalpy change here, that is the reactant, it as it is at greater energy as compared to product, that means we will get a delta H negative. Now we know very well that if delta H is negative, it is a exothermic reaction, that is energy is released during the reaction. So from the reaction profile you can predict many things, like what is the transition energy of transition state and how many transition state are possible. So we will see later how it is depicted using the energy profile. Then we can also see whether the reaction is exothermic or endothermic, or if we are comparing two reactions, then you can see that which one will require less energy to proceed. So you can acquire very much knowledge about this any reaction using this reaction profile. So this reaction profile will be very helpful in the organic chemistry also. In some places like for SN1 and SN2 you will see different reaction profile. So let us move to the next advanced level of this reaction profile. So let us consider another reaction profile like this. So it is for a reaction that is given as A that goes to I then to B. So if you want to consider an example, you can think of it as a SN1 example, SN1 reaction, in which first the formation of carbocation that takes place, that is the intermediate, and then we get the product, that is B. So this is the energy profile diagram. So first the reaction goes from A to the transition state 1, okay, and some energy falls down, that we get the intermediate here. Again the reaction proceeds to the transition state 2, and finally we get our product. Now the thing that is to be looked here is that there are two kinds of activation energy, which are EA1 and EA2. So these are the two activation energy, and here is the intermediate. So how do you catch an intermediate during a reaction? It is just a valley. You can see very clearly that it is a valley here. So you can see a kind of valley formation in the this, and this valley formation, the very minimum of this valley formation represents the energy of the intermediate, and this is the reactant again and the product, and this is for this hypothetical reaction, that is A goes to I goes to B. Now let us see some of the points of this, that this is the transition state or the first transition state TS1, this is the second transition state TS2, it is activation energy EA1 and activation energy EA2. So why am saying all of this? So maybe it would not help you in this chemical kinetics, but later on when you will study the organic chemistry and you will see that what is SN1 reaction and SN2 reaction, then there will be similar kind of diagram for SN1, and for SN2 the previous diagram will be applicable, because in there no intermediate is formed, only one transition state is formed. So this is the you can say a brief description of this reaction profile. Now we will use this reaction profile knowledge and see that what is the effect of temperature and catalyst, because it is much easier to see the changes using this reaction profile rather than having a theoretical knowledge. So graph are much more helpful in this way. So what is the effect of temperature? So this was given, or you can say quantified, by the Arrhenius theory. So it was quantified by the Arrhenius theory, and he only gave the idea of the activated complex, that okay, the reactant will get some energy move to the activated complex or the transition state, and then will give the product. So it is an idea of Arrhenius only. So Arrhenius theory, we know the Arrhenius equation very well. That is relating the rate constant with temperature. So it is written as K is equals to E into minus EA by RT. Okay. Now what are these terms? K, so you know very well this is rate constant. This is called as the frequency factor or the pre-exponential factor. So it has two names, so do not get confused if some other name is said that, okay, so suppose in a question you are given that the frequency factor of something is this. So it is nothing but the pre-exponential factor or the value of A. Then we have R, that is the gas constant, and T, that is the absolute temperature, and EA, that is the activation energy we have seen earlier. Okay, so this is the activation energy only. Now you can see very clearly that through the equation also that suppose the value of T goes up, so this whole value EA by RT will go down, then this E to the power will go up. Okay, so in this way you can say that as the temperature rises, the value of K rises or the rate constant rises. So we will see more accurately through the graph. Then we will may more specify this equation you taking the natural log on both sides. So for now we will consider that on increasing the rate constant, the increasing the temperature, the rate constant value increases. Okay, so why is it so? If you see the equilibrium constant, so equilibrium constant is nothing but the ratio of the back forward reaction by backward reaction. Okay, that is it. So if you see that, you can see that K is dependent on this rate constant, and we know very well that equilibrium constant almost depends upon temperature. You can say it only depends upon temperature. So this rate constant also does the same. But there are some peculiarities, so we will see it later on. So this is a graph of ln k versus 1 by t. So how do we get this graph? Let us see. So we know this equation, that is k is equals to a into minus ea by rt. Now if we take ln on both sides, then we will get this equation, that is ln k a minus ea by rt. So those who are confused, how do we move to this equation from here to here? Let me show it to you. So it is written as k is equals to a e minus ea by rt. So I have told you three rules of logarithm, or you can say four rules particularly, including the ln is equals to 2.303 log. Okay, so if you take the ln here, so that will give us ln k a e minus ea by rt. Now we know very well that ln a into b is equals to ln a plus ln b. So we will write this equation further as ln a minus ln e to the power, sorry, this will be plus minus ea by rt. Now further we know that ln x to the power n give us n ln x. So we'll write this equation further as ln k is equals to ln a plus minus ea by rt ln e. Now we know that ln e is equals to, suppose, x, then e is equals to 10 to the power, sorry, e to the power x. So this is the equation we know very well. So when it will be e is equals to, so when x is equals to 1, we can say that. So ln e value is, sorry, so suppose we have this value, then it will be x to the power, so this is the equation, then a is equals to e to the power x. Now it is saying that we have e here. So when it will be e? When x is equals to 1. Therefore we can further write this equation as ln k is equals to ln A. This minus plus will be minus EA by RT. Okay, so this is the final equation we have here. So the same equation is written here also, that is ln K is equals to ln A minus EA by RT. So further, we have studied about graphs in the previous class. So we know from the equation of straight line that y is equals to mx plus c. So if you rearrange this equation in the form of this equation, then you will get the value of y as ln k. So this is the value of y, that is ln k, and the intercept, that is ln a, which is constant, is equals to c. Then we have that 1 by t, which we are varying. So this is the variable here, 1 by t, which is x here, and then we are remained with this slope of the reaction, that is the constant minus EA by R. So this is the slope of the reaction. Now you can see very clearly that the slope is having a negative value. Why? Because activation energy is always positive. Okay, so remember this thing. So why? Because we know that we are constructing a transition state, and transition state is always less stable. Okay, so for that reason, and we know that the reactant which you are taking must be stable. That's why we are taking that as a reactant. So it will go from a reactant to transition state. It will require and always require some energy. So this activation energy will always be positive. Now this gas constant value is fixed, which is 8.314. So positive divided by positive will be positive. Now if we put a negative sign here, then the whole slope or the value of m will be negative. That is why we get a curve which looks like this, having a negative slope and have an intercept of ln a, and we are plotting a graph of ln k and 1 by t. Now you can see very clearly from the graph that if we are increasing the value of 1 by t, the value of ln k is also decreasing. So let me show you here. So it is saying that as the value of ln k is decreasing, or you can say as the value of this 1 by t is decreasing, the value of ln k is also decreasing. Now what we can further infer from this graph, so if the value of this 1 by t is if t value of 1 by t is increased, 1 by t is increased, sorry for the mistake. So as we are increasing the value of 1 by t, the value of ln k is decreasing. Okay, so you can see here clearly that as we are moving the value of 1 by t, the ln k is decreasing. Okay, sorry for the confusion. So as we are increasing the value of 1 by t, this ln k is decreasing. Okay, so what we can say that if we increase the value of temperature, then the value of ln k will also increase. So it is very pretty much sure about this, that of course if 1 by t is increasing, that ln k is decreasing. Now if we take the opposite of it, or the reciprocal of 1 by t, and if we will increase it, then ln k will also increase. Now we also know that k is directly proportional to ln k. We know it very well, because as we take the value of greater value of ln, k, the value of ln k will increase. That means this t is proportional to k. Proportional you cannot say. So as the temperature T will increase, this K will also increase. So from the graph we can clearly predict that yes, if we increase the value of the temperature, then the value of rate constant will increase. So keep this thing in mind, then we can proceed to next part. Okay, so we have defined it from the formula that yes, we can just increase the temperature, increase the value of the rate constant. Now if we increase the value of the rate constant, then of course the value of rate will also increase, because we know that R is equals to K into concentration, and concentration is raised to some power which is equals to the order of the reaction, that is the rate law we have. So according to rate law, if we increase the R, we will increase the K also. So how does this K change? If you want to get a more qualitative information about it, let us define it using a new, you can say, observation that was made by the Boltzmann. So it is called as the Boltzmann distribution. So it is for the complex, but just to give you an idea, I have taken this from NCRT. So it is just taking the output of this equation only, and then plotting this graph. So it is the plot that is made using this, say, Boltzmann distribution. So what is this basically? It is the distribution of the particles with change in temperature with change in temperature. So it says that how does the number of particles that is in an energy state will change with change in temperature. So if you see here, you can see very clearly that this fraction is what? So this is called the where the dn by n is the number of molecule having the velocity between v to v plus gv. So it is basically saying that what is the fraction of molecule that is the having the say velocity that is between v to v plus dv, and it is given as e to the power. So we will not concentrate all this constant because this whole value is a constant. Why? Because mass is constant, Boltzmann constant is also constant, temperature. Okay. Okay, yeah, one variable is there, so we will take it as constant, excluding this temperature. So let me exclude this temperature. Okay, so we have this dn by n depends upon 1 by t e to the power minus 1 by kt. So this all things are also constant, this v square and all. Now if you infer to this equation, you can see that as we increase the temperature, the fraction of molecules having greater energy will increase. So if you just simplify this equation, you will get it very easily. So not let us make this thing complicated. I have just mentioned this equation so that you can see from where this graph comes. Okay, so if you just look at this graph here, you can see that this is the graph of the fraction of molecules having energy, this energy profile for t plus 10, and this is for only t. So what we are doing is that we are plotting two graphs, first at temperature t for the fraction of molecules having kinetic energy something, and at t plus 10. Now if you look at this graph more clearly, or you can say more specifically, you can see that okay, what has been changed? You can see that first of all, the fraction of molecules having a particular energy is changed. So we do not have any, it do not have any effect on this, say, this equation, that is k is equals to e to the power minus a by rt, or the rate of equation. So this is the thing, that the molecules having the part of this energy has decreased, but it is the lower energy, and we know very well that to form the transition state we have to look into higher energy. So in higher energy, if you infer here, then you can see a slight change. So at temperature t plus 10, some of the molecules having higher energy is increased. So this is the thing that I want to make point here. That as we increase the temperature, of course, the you can say the species having low energy have decreased, but the species having a higher energy is increasing. So this is a small change in that. Now this is the case. Now you can see that of course the fraction of molecules having high energy have increased. Now this will result in a greater amount of molecules, or the probability of the molecules, reactant molecules going to the reactant have increased due to this increased kinetic energy of the fraction of molecules. Okay, so this is the reason that the rate of reaction also increased, because the rate of reaction, it says that it is the change in concentration of product with respect to time, or the negative of change in reactant. So if the probability of reactant going into molecule has increased due to the increased energy, then it will have a greater rate of reaction. So in this way Arrhenius explained this thing, the rate increase with change in temperature. Okay, so overall point I want to make here is that as we increase the temperature, we increase the rate constant, and do we increase the rate of reaction also. But I am not mentioning whether the reaction will rate of reaction will have a a greater change in the forward or in the backward case. So in case of reversible, what does happen is that the rate of forward and backward reaction changes or increases with increase in temperature simultaneously. So that's why you can say, let us see, we will make it more clear using a graph. Okay, so let us more define this Arrhenius equation. So if we take the Arrhenius equation at two different temperature, say at temperature T1, then we will write it as ln K1 minus EA by T1 into ln A. Okay. Now at temperature T2, it will be ln K2 minus EA by RT2 plus ln A. Now the thing is that this ln A, or the frequency factor A, will not depend upon temperature at all. Okay, so keep this in mind. So at temperature T1 it will be only A, or at temperature T2 it will be A only. So there will be no change in this thing. Okay, now next, if we subtract this both of these equations, so subtracting both of these equations, that is ln K2 minus ln K1, so you will get this final equation. So if you want, you can just derive it also. It is written as ln K2 is equals to minus EA by R T2 plus ln A. And for K1, we can write it as minus EA by R T1 plus ln A. Now if we subtract both this equation, that is ln K2 minus ln K1, now this thing are same, so they will get cancelled, and we'll get this value as EA by R 1 by T1, sorry, 1 by T1, okay, minus 1 by T2. We will get this equation. Now we know that ln A minus ln B can be written as ln A by B, that is ln K2 by K1. So this same equations is written here. So further, if we just cross multiply and take the LCM of both of this, then we will get as T2 minus T1 by T1 T2 is equals to ln K2 by K1. Now this equation is very helpful. So many numericals will be asked based on this. You will be simply given that, okay, just this is the temperature, both of the temperature, and one of the rate constant will be mentioned, and also this activation energy is mentioned. So we'll just put the equation formula and you will find your answer. Now if you further you can say simplify this formula, put 2.303 log instead of ln, then it will be this equation. Okay, so this was the derivation for this equation. Now let us move to the effect of catalyst. Okay, so this is a very this is a very confusing thing for most of the student, that why catalysts do not change the rate of reaction and all, so means the rate constant and all. So this is the answer. So it is hidden in its energy profile diagram only. So say we have two kinds of curve. So the first one is without catalyst, and the second one is with catalyst. Now what do we see that the change that has occurred is that we see a different path is being followed in case of catalyst involvement. Okay, so as the catalyst involved in the reaction, this thing has followed a different path. So the reaction has followed a different path instead of this one. Now if you want to make the more easier this energy diagram reading, then consider in your mind that we are riding a cycle and we have to go from this point to this point, and we want to make it more easier and easier. So suppose if you cycle from here, then you have to paddle more to move to this part, rather than you can take an easier path which is in down one, and you have to travel a less you have to travel a path that is having a less slope. So you will of course follow this path, so that you require less energy to complete this path. Okay, so consider it like this. Now if we put this catalyst, they provide a new path like this. Now the reaction rather than moving to this part follows this one. Okay, It follows this one, and there is some kind of activation energy drop here. So we know very well that without catalyst, this is the EA1, that is the activation energy without catalyst, and this is EA2, that is activation energy with catalyst. So if you mention it here, this is EA2 and this is EA1. Okay, so this is daily EA, that is EA1 minus EA2. So it is mentioned here also activation energy with catalyst and activation energy without catalyst. Now if you see here, that why does the equilibrium constant does not have any change due to this involvement of catalyst. So it has of course reduced the energy requirement for reactant to go to product, but at the same time it has decreased the same amount of activation energy from going to product to reactant also. So I mean to mention here that of course the rate will change, the rate of reaction will increase, but it will increase for both of the paths. Now due to this reason, the forward and backward rate of reaction increases in the same amount, and there is no net change in the equilibrium constant on the involvement of catalyst. So this is the very basis of defining that why this catalyst is having no effect on the potential energy change, sorry, the equilibrium constant. Okay, so this is the reason. So because it is having the same amount of change, the forward rate of reaction and the backward rate of reaction are having the same amount of change on introduction of the catalyst, because they provide a lower path for both of this reactant and product. Okay, so this is the explanation for the effect of catalyst. Now let us see some points, so you should keep this in mind. The first is that catalyst only lowers the activation energy. It does not change anything at all. It only changes the activation energy, or you can say it provides a different path for the reactant to go through so that it can form the final product. The second is that a catalyst does not alter the Gibbs free energy. So keep this in mind always. So suppose what are the effect of this? So why I'm mentioning it here, because it catalyzes the spontaneous reaction also. So if it has suppose changed the delta G in some way, then it may include that, or you can say it can affect non-spontaneous in some cases also, because delta G only defines whether reaction will be spontaneous or non-spontaneous. So if catalyst was able to change this delta G, then it can change from a reaction that is spontaneous to non-spontaneous, or non-spontaneous to spontaneous simultaneously, but it is not so. So a catalyst only catalyzes the spontaneous reaction and does not have any change, or it cannot catalyze any non-spontaneous reaction. So keep this in mind always. Okay, so this is a very important point, this three. Now this is also an important point for remembering why does not alter this equilibrium constant, because it is changing the rate of both forward and backward reaction. So the net change on the equilibrium constant is 0. And also we know the relation, since we are saying that delta G is minus RT ln K. We know this equation very well. So K is not changing, delta G is not changing, and vice versa. Okay, so this was all about the effect of catalyst. Now let us move to the last theory. So we have studied two theories regarding this reaction rate. The first one was Arrhenius, in which he defines the temperature dependence and also says that there is a formation of say we activated complex during the reaction. But in the collision theory, some more points were included, which says that okay, only the energy having enough energy is not possible for a reaction to occur. There must be a proper orientation. Okay, so this is the important point that was put forward, or that was put forward by this collision theory, that okay, they must have the required energy. At the same time, they must have a proper orientation, so that the overlap of these orbitals may take place efficiently and result in the product formation. So we have two cases here. Suppose this is OH having a negative charge and it attacks on this Br, that is delta negative. Now since we know from the very basic idea of this electrostatic force that like charges repel each other, now having this same charge, it will repel each other. So we are not going into the say orbital orientation, we are just defining it, or you can say we're just simplifying it using the electrostatic force of attraction that is in the NCRT. So we are just combining of both of this in the opposite fashion, that sorry, in the same charges, so that's why they will repel each other and no product would be formed. So this is the first case we have. Now if you take a proper orientation such that this Br minus attacks and it interacts with this carbon which is having a delta positive sign, then only the required product, that is this methanol, we will get. Okay, so this is a very simplified version of this collision theory using the electrostatic force of attraction, or the using the electrostatic principle. We are simply defining this collision theory. Okay, so many more factors are there like the orientation of orbitals and all, but we will not go into that. We will just see a glimpse of this collision theory. Now this is the formula that has been derived using this collision theory, that is given as Pze to the power minus E by RT. Okay, now what is this P? This is the steric factor, so it must orient, or you can say attack, in a certain manner so that we will get this steric, you can say this we can get this product. So this defines this steric factor. You know very well this part. It defines the temperature, or you can say energy part. So there should be a particular energy, and sorry, and there should be a particular orientation. And the third one, that is simpler one, it is the number of collision per unit volume. So collision must be occurring to get our product. So we will so three parts are considered here, three factors. First of all, the collision must take place. Second, in proper orientation, and third, with sufficient energy. So these are the three components of this collision theory. Okay, so these things are mentioned. You must be aware about this points, that okay, this is collision frequency, this is steric factor, this is activation energy, and gas constant, and temperature, and all. So just remember this formula in case you are just given the values of all of this, you have to calculate it, and it will be very easy to do so. Now just for a knowledge, this is the formula for the collision frequency. You do not have to remember it. It is written in terms of average, average kinetic energy, average velocity, and all. So this is the formula. Okay, this is the extra slide we have. Now let us move to our questions. So we will solve some questions, or 10 questions. So 5 questions I will solve, and 5 questions you will be solving. Okay, so that you can get a clear grasp of this concept that I have taught today. Now let us start some questions. So what is the role of catalyst? So I have given the points also. So I put a theoretical question so that you do not forget this concept. So it changes the Gibbs of energy? No. Not. It changes the enthalpy of reaction? No. It changes activation energy. So this is right. So enthalpy of reaction is also not changed, because only the say we are putting down the energy of the activated complex down, but the energy of reactant and product is on the same phase. So it only changes the activation energy of the constant. Equilibrium constant, we have defined it very well, that it changes both rate of forward and backward reaction. So the net change is defined as the equilibrium constant, so there will be no net change, and hence no change in equilibrium constant also. Now let us move to our next question. Okay, so question number 2 we have here. So it says that a reaction of a rate doubles when its temperature changes from 300 to 310 Kelvin. The activation energy of such a reaction will be so we are given two cases. Suppose the first case is said that rate of reaction doubles. So if you are initially having a 300 Kelvin, then the rate is R. Then at 310 Kelvin, the rate is 2R. Now you have to say that what is the activation energy. Now let us see the solution. So as per Arrhenius equation, we know very well that ln K2 by K1 is equals to minus EA by RT. Now if we increase the rate of reaction by 2, then the rate constant will also change by 2. So keep this in mind. Okay, so if we put this value here, so K2 is equals to K1, K1 is equals to 2K2. sorry, K2 is equals to 2 K1 when K2 is for 310 and K1 is for 300. So this is the value we have. So if you put it here, you will get is ln2, which will be 2.303 log 2. Now activation energy value we have to find. Temperature is given 300 310. We'll put those. We know the value of R, that is 8.314. So if we calculate it, you will get the activation energy value, that is 53.6 kilojoule per mole. So this is our final answer. Now let us move to our next question. So it says that a reactant A form two products, that is A to B, having energy K1 and K2. So two rate constant are there. If EA2 is equals to 2EA1, then what is the relation between K1 and K2? So it is very easy. You can solve it. So we have two reactions that are A to going to B from having a rate constant K1 and A going to C having rate constant K2. Now if we write the radius equation for both of this, then it will be K1 A dash e to the power minus E1 by RT and K2 A dash EA by e to the power minus A2 by RT. Now the thing I want to mention here is that we have seen that temperature has no change on the frequency factor. Also, the frequency factor for the forward and backward reaction is same. So this should be kept in mind. So I have not put some points, so let me write it here. So I am writing because you can get a clear idea. So A is independent of T and same for backward and forward reaction. Okay, so keep this in mind always. So this is a very crucial point. Okay, now if you write the rate constant using this concept in mind, then it will get this. Now further, A is constant for both of this. You will just equate those equations and you will get the final equation as K1 is equals to K2 e to the power minus E1 by RT. Now let us move to our fourth question. So it says that consider the RNS equation which is given below. K is equals to A to the power minus A by RT. So what can we infer from this equation? So the rate constant increases exponentially with increasing activation energy and decreasing temperature. So it is absolutely wrong. So we know very well that as we increase the temperature, the rate constant will increase. So it is wrong. The rate constant decreases exponentially with increasing activation energy. Now next one. Rate constant increases exponentially with decreasing activation energy. Okay. And decreasing temperature. So it is also wrong. Rate constant is increasing exponentially with decreasing temperature and increasing temperature. Okay, so this is right. That rate constant increases exponentially with decreasing activation energy and increasing temperature. So why am exponentially? Because we know the relation between them, that is exponential. So K E. So if you write this equation as this, we keep all those things constant. Suppose we write it as A. Okay, so this is constant only. So if we vary the temperature, that is the X, and if we keep all these things constant, it will be C suppose, then we can see very clearly that it will increase exponentially on increasing its temperature. Why? Because it is e to the power minus then 1 by T. Okay. Now if we see this second thing, that is increasing the activation energy, which is not possible. We are taking a hypothetical condition here. Okay, so do not get hyped that why we are changing the activation energy. It is just the ask of the question. Okay, so if we write similarly, we can see that as we will increase the activation energy, this value will increase and this whole value will decrease. So we will see a exponential decay of this value of K as we increase the activation energy. So this is the explanation for this. So this is the correct answer, that is D. So the same thing is written here. Okay. Now let us move to our next question. So what does this question says? So it says that we have this equation that is given as log k is equals to 5 minus 2000 by t. So this is nothing but the a form of this say a form of this equation, which is ln k is equals to ln a minus e by rt. That is the Arrhenius equation. Now the one thing I want to mention here is that if we put a log here, then it will be 2.303 log k small k ln a minus e by rt. Okay, so consider the following about this equation. So let us see what are the points that are made here. So the first statement says that pre-exponential factor is 10 to the power 5. Second statement says that EA is 9.212 calorie and variation of K with 1 by T is linear. So let us verify this all of this. So let us find A here. So if you see here, then you can see very clearly that we have the L log K value. So we will further write this equation as ln A by 2.303. Okay, so it should be clear. So do not make the mistake, but it is a very common mistake children do. Okay, now what is the value that is given? It is 5. Yes, this is 5. Now we know that ln A can be written as 2.303 log A. So we can write it as 2.303 log A by 2.303. Now what is the value that is given of all of this? It is given as 5. Now this will get cancelled and we will get the value of A is 10 to the power 5. Okay, so this is correct. So statement 1 is correct. Now what about EA? So if you see here, so let us take a different page. Okay, so it will be written as log k is equals to ln A by 2.303 minus EA by 2.303 RT. Now what is the equation we have here? It is given as log k is equals to 5 minus 2000 K Kelvin by temperature. Now if we equate both this equation, we will get it as EA by 2.303 R T is equals to 2000 by T. Now this T and T will get cancelled. Now if you further solve this equation, that is EA is equals to 2000 into 8.314 into R and this is 2.303. Now if you solve this, you will get your answer. So you can check that whether it is 9.212. So it will be solved in the later slides also. So do not worry. So don't worry. Now what about this last statement that we have here? So it says that the slope, the variation of log k with 1 by t is linear. So we have seen earlier also. So if you see this graph, so if you see it, y is equals to mx plus c. So if you compare it with this equation, you can see very clearly that y, this is L log k, and x, which is 1 by t. So it gives the equation of a straight line, although it has a negative slope, but it is linear. Okay, so this is also correct. Okay, so third statement is correct. First is correct or not, we will see in the later on slides. So this is the value. So it is true. First is true. Now if you find the second, you will get it as same. That is 9.212. Okay. Now we have taken a value of calorie per mole. So those who do not know what is the value of R, it is 2 calorie. In terms of calorie, it is 2 calorie, the value of R. So if you write in terms of kilocalorie, it will be 2 into 10 to the power minus 3 or 0.002. So if you solve this, you will get this as final. So it is also true. and the third one is also true. So all these equations are true. So 1, 2 and 3 all are true. Now I've solved 5 questions. Now I will just pass on the question and give you a little hint. You have to solve it by yourself, the remaining of the questions that we have. So the next question that is asked here is that for the reaction following data is given, so A to B and C to D, at what temperature K1 and K2 will be equal? So it is a very simple question. So you will just equate both of this equation and you will get your temperature very easily. So it is not a mess. Okay, so we can do it. Now next one, two reaction R1 and R2 have identical pre-exponential factor, that is the value of A is similar for R1 and R2 reaction. The activation energy of R1 that of R2 is exceed by 20 kilo joule per mole. So R1 minus R2 is given as 20 kilojoule per mole. If K1 and K2 are the rate constant, then what we have to find is that ln K2 by K1. So we know the formula very well, that is ln K2 by K1 is equals to EA by 2.303 R, then T2 minus T1 by T1 into T2. You will put all those values, T1, T2, we have the value of EA also, and we will find the final answer, that is the ln K2 by K1. Okay, so this is the exercise, you must do it. Now next question we have, so it is a statement type question, which says that a collision between a reactant molecule must occur with a certain minimum energy before it is effective in yielding product molecule. Okay, so this is the first statement that is made. So you have to say that which is the correct one. The second one says that d log by dt is equals to EA by 2.303 RT. So we know that log K is equals to uh, log A, sorry, ln A, K is equals to ln A minus EA by 2.303 RT. Now if we just take a differential of that and then ln A, which is a constant, it will be 0, then we will get this equation only. So this one is also correct, the first one is also, the second one is also. So you must solve this equation to get your final answer, then only you will see that it is are different to solve. Okay, so both A and B are correct. Now consider the next statement, which says that for an endothermic reaction where delta H represent the enthalpy of reaction, the minimum value of the activation energy will be. So it is kind of comparative study between this A and delta H. So you will just have to draw this graph first of all. So for this kind of question, first draw the graph. So it is saying that for the endothermic reaction, so since it is an endothermic reaction, the reactant will be at greater energy than the product. The minimum value of delta H, where the delta H represent the minimum value of the energy of activation, will be what? So we have to find the minimum value of energy. So you will do it by yourself, because it's the theoretical answer which will give you answer in one sentence only if you know the concept. Now the last question of today's, that is the plot of log k versus 1 by t is linear with a slope of. So I have solved it for you, but you must do it one more time because it is having a slight change in it. The graph I have showed to you was of ln t versus 1 by t, and it is log k versus 1 by t. So if you solve it, you will get a different value. Okay, so these are all the 10 questions that we have. So thank you for today's time. So tomorrow we'll start a different chapter. Okay, thank you.